Okay, welcome back. This week we're going to be doing parts of two different chapters, chapter 3 and 23 on matter and minerals. So what are minerals? Minerals are the building blocks of rocks. By definition, a mineral is something that's naturally occurring, an inorganic, solid, ordered internal molecular structure, which means the atoms have a set structure to them, and a definite chemical composition. And then a rock would be a solid aggregate of those minerals. Now, the composition of minerals includes elements and atoms, and elements you've learned in school. From the periodic table, there are the building blocks of minerals. There are less than 100 known, 92 of them are naturally occurring. Atoms are the smallest particles of matter and retains all the characteristics of an element. The structure of an atom is such that the central part is called the nucleus, contains protons and neutrons, and outside the nucleus is a cloud of orbiting electrons. And I'll show you a diagram of that. The electrons orbit in particular shells around the nucleus. So here we see the red are protons. They have a positive charge. Neutrons have no charge, are blue, and orbiting that in their various clouds are the electrons, which have a negative charge. Now we can determine the properties of minerals by doing some simple testing on them. Several physical properties are used to identify hand samples of minerals, and you'll be doing this in lab. We know that some minerals have a crystal form to them, and they originate their atoms in certain structures. Here is a picture of pyrite. You can see that it's structured in a very particular way. With all minerals, we can talk about the various physical properties of them, and there are 6 of them. The first one is luster. Luster is an appearance of a mineral in reflected light. It can either be a metallic or a non-metallic luster. So here is Galena. This is found in Missouri, and it displays a metallic luster. You can see how it shines like a piece of metal. Color is the second mineral property. Generally unreliable for mineral identification, so we don't use it very much, and it can change over time. So here are a variety of different colored of quartz, so you can see how the different colors blend in. The next 2 properties are streak and hardness, and you'll be testing these in the lab also. Streak is the color of a mineral in its powdered form. Usually we can take a piece of a ceramic plate and streak it across it and get a color of it as it's disintegrated on the plate. Hardness is the resistance of a mineral to abrasion or scratching, and we identify the hardness based on a scale called Mohs scale of hardness. So here is a mineral being scratched onto a ceramic plate, and the color of that scratch will identify it. Here is the Mohs scale of hardness. It goes from 1 to 10, 1 being easily scratched, so you have talc and gypsum and calcite salts, all the way up to number 10, which would be a diamond. Now, for comparison, a wire nail, for instance, is a 4.5, a penny is a 3.5, your fingernail is a 2.5. Another property of minerals is cleavage. This is the tendency to break along planes of weak bonding. Produces flat, shiny surfaces and can result in various geometric shapes. So here we have different cleavages of different minerals, from muscovite to feldspar, hornblende, halite, calcite, and fluorite. They have various cleavages to them, as you see here in the diagrams. Probably the most common cleavage you'd see is with calcite, fluorite, and halite, how it breaks into certain cubical and sheet-like structures. Mica, which is, there's two types of mica you'll see in your lab packet, is like in sheets. And so it can be easily split apart into thinner sheets, almost like the thickness of a piece of paper. And then we have fracture. Fracture is the absence of cleavage when a mineral is broken. And specific gravity, which is the weight of a mineral divided by the weight of an equal volume of water. Here is a conchoidal fracture. You can see that it doesn't have a certain cleavage to it. Other properties of minerals that we like to use is if they're magnetism, if they're magnetic. Reaction to hydrochloric acid. We know that in Missouri we have lots of limestone, and limestone will make hydrochloric acid bubble up. Malleability, can you manipulate it in your hands? Double refraction. Taste, halite, which is salt, tastes like salt. Kind of a nasty thing to do in lab. Sometimes you'll get students in lab and they'll lick the piece of halite to see what it tastes like. And you've licked it after thousands of other students have licked it. Smell, will smell a certain way. And elasticity. Now we know of nearly 4,000 minerals have been named already. We have the rock-forming minerals that make up most of the Earth's crust, and that's only a few dozen members. Mostly composed of 8 minerals, elements, that make up more than 98% of the continental crust. So here we see our crust is mostly, believe it or not, oxygen, 46%, silicon, 27%, and then we have a variety of others that are just a few percentage points: iron, magnesium, potassium, sodium, calcium, aluminum, and other elements. Now we have certain groups of minerals. The silicates are the most important mineral group, and these are the most common rock-forming minerals. Silicates are very abundant due to the large percentage of silicon and oxygen in the Earth's crust, and the silicates form a silicon-oxygen tetrahedron structure, and we'll show you that here in just a second. Fundamental building block of rocks: 4 oxygen ions surrounded by a much smaller silicon ion. So let's take a look at that. Here we have the 4 oxygen atoms in a tetrahedron with the silicon in the middle. Very, very common in the Earth's crust. Very important to memorize this. We'll leave it up on the screen for just a second. Again, the oxygen is in a tetrahedron order with the silicon in the middle. We're going to pause the video at this point now and switch over to chapter 23 notes. And so here we are back with chapter 23 notes on energy and mineral resources. We have renewable and non-renewable resources. And so the renewable resources can be replenished over a relatively short time span. These include things like plants, animals for food, and trees for lumber. And then the non-renewable resources. These are significant deposits that take millions and billions of years to form. Examples of this would be fuels: coal, oil, and natural gas, and various metals like iron, copper, uranium, and gold. Some resources, such as groundwater, can go in either category depending on how they are used. So in the United States, here's our energy consumption. 37% of it is petroleum, 24% natural gas, 23% coal. A smaller portion, 9%, is nuclear power. Most of those nuclear power plants are near the East Coast. And then only 7% are renewable energy sources. And of that 7%, over half is biomass. A little bit is wind, a little bit is geothermal, hydroelectric from water going over dams, and just 1% is solar. Now, I recently took a trip to Arizona, and while flying over west from Texas, I saw a huge wind farm where they had about 250 wind turbines blowing in the wind, generating enough electricity to power a whole city. We also have Table Rock Dam and Bagnell Dam that generate hydroelectric power in the Ozarks. Near Las Vegas, you have Hoover Dam, which powers much of the western United States. Coal is formed mostly from plant material. Along with oil and natural gas, coal is commonly called a fossil fuel. The major fuel used in power plants to generate electricity is coal, and if you're familiar with Springfield, we use a coal-powered power plant. Problems with coal use include environmental damage from mining and air pollution. So here are various coal fields in the United States where we tend to find coal. A lot of it here in the Midwest and along the Appalachians. Oil and natural gas, consisting of various hydrocarbon compounds, are found in similar environments. These are derived from the remains of marine plants and animals from millions of years ago, and the formation is complex and not completely understood yet. And so a geological environment that is sufficiently allowable for oil is called an oil trap. And common oil and natural gas traps include anticlinal traps, fault traps. Here we can see the different traps we can find oil in. First, topographics of the earth. And so you might have to drill through some rock and get through the gas and water to get to the oil. Of course, oil floats to the top of the water. Carbon dioxide and global warming. Burning of the fossil fuels. We know burning fossil fuels produces carbon dioxide, which is one of the primary gases responsible for warming the lower atmosphere. CO2. What is the greenhouse effect then? The atmosphere is transparent to incoming short wavelength solar radiation. However, when it bounces off the Earth and leaves, it goes into a long wave radiation, which is emitted by the Earth and absorbed in the lower atmosphere, keeping the air near the ground warmer. And we do know that since the Industrial Revolution around the 1780s, that the increase of carbon dioxide has gone up significantly, and especially within the last 50 years, it has really started to go up exponentially into a very high spike. And now we are at the point where we have reached 400 parts per million of carbon dioxide in the atmosphere. It appears that global temperatures have potentially increased, global warming of course, due to a rising level of atmospheric carbon dioxide. Certainly there are other factors that would probably come into play of global warming, but we do know that the increase in carbon dioxide does seem to play a role in this. Now, the alternative energy sources include 90% of the world's energy needs derived from non-renewable fossil fuels. These are possibly including nuclear energy, solar energy, and wind energy. Solar energy is very common in the West Coast, where they have lots of sunlight all the time. So here's a solar plant near Los Angeles, and these mirrors reflect the sun's light. Sometimes they reflect these lights into a collector you see there. The collector has water in it sometimes, and that heats the water to super hot temperatures. And that generates electricity. So here's the wind energy around the United States. The blue is excellent wind energy areas. Green and yellow are moderate to good. And like I said, I flew over western Texas and saw a wind farm. They had about 18, 19 turbines in a line with maybe 8 or 9 lines worth of turbines, and they were all blowing pretty fast. Alternative energy sources include hydroelectric, like with the water dams, geothermal energy, using the temperature of the earth to generate energy, and tidal energy through the ocean tides. Mineral resources include reserves, which are already identified deposits from minerals that can be extracted profitably, and well-known deposits that are not economically or technologically recoverable. An ore refers to useful metallic minerals that can be mined at a profit, and in common usage to some non-metallic minerals such as fluorite and sulfur, and for them to be considered of value, an element must be concentrated above the level of its average crustal abundance. Some of the most important oral deposits are produced by contact metamorphism, which means that the contact of pressure and heat leads to these minerals, such as zinc, lead, and copper. So that's it for minerals. Be sure to read chapters 23 and 3 in the book, and I look forward to your discussions.